So now let's look at the planets we have discovered. The first weird thing that we discovered is that a lot of extrasolar planets have very elliptical orbits. So our solar system here is shown in yellow. Our planets have nearly circular orbits, which we reasoned out made sense if they formed from a spinning disk. And we're pretty darn sure that all these other planets formed from spinning disks as well. So we were surprised by all of these elliptical orbits that we're finding. Here's a graph from exoplanets.org showing the average orbital distance from the Sun versus orbital eccentricity. And so all of our planets in our solar system should be close to zero, nearly circular orbits. So we've got Earth and we've got Jupiter. And it's surprising just how many planets have amazingly elliptical orbits. In our solar system, we were easily able to sort the planets into two categories, terrestrial and Jovian. And now that we're looking at all of these other planets and measuring their properties, we're having a hard time fitting them into those two categories. So let's go through this figure from your book a little bit. So it plots planetary mass along the horizontal axis. So low mass planets would be over here. The highest mass planets are over here. And on the vertical axis you have planetary radius. So since we're comparing mass and radius, we're also looking at the density. So you've got this line here, which represents the density of styrofoam, the density of water, and the density of iron. So we've detected planets that have the average density of styrofoam, planets that have the average density of iron, which is, in both cases, very impressive. And we're going to add in some new categories as well. We can have metal-rich terrestrial planets with rock and metal. These are going to be called water worlds, planets rich in hydrogen compounds. So actually, we're renaming Uranus and Neptune to be called water worlds. Right? Don't picture them having oceans, but they are mostly made up of water, methane, and ammonia. And then you've got your typical Jovians, right, which includes Jupiter and Saturn. And these are going to be the hot Jupiters, the ones I mentioned before. And they're going to be a larger radius than we would expect Jupiter to have. It's because they're hot. And you make a gas hot, it'll swell up. It'll have a bigger radius. Notice these images here. A lot of these images are going to be art, because I showed you how good of an image we can take of a lot of these planets, right? And we've never seen a planet better than just a fuzzy dot. This was a very excellent chart that I found, and it's based on the Kepler mission. This part up here shows you how many planets we have found per system. So systems with only one planet, we found about 3,000 of those. With 2 planets, with 3 planets. We found almost 60 candidates with 4 planets, all the way up to 7 planets around one star. This figure uses different terminologies than your textbook, but they had mini-Terrans, so those would be smaller than Earth. Sub-Terrans, still smaller than Earth. Earth-sized planets. Super-Earths, right? So terrestrial but more massive than Earth. These are those water worlds, and your Jovians. And then this figure breaks them down by hot zone, too close to your star to have liquid water. Habitable zone, which doesn't mean that we know it's habitable, it just means we think it could have liquid water. And the cold zone definitely doesn't have liquid water, it would be frozen. Right? So it's kind of fun just to look through here and see how many of each category we've discovered. So let's mostly look here at Earth-sized in the possibly habitable region. 26. You could also live on a sub-Terran or a super-Terran. So possibly over 100 candidates that might be habitable. Okay. And notice these pictures here representing the categories. Those are just art. Right? We cannot see an extrasolar planet that clearly. So now that we've found some odd planets and some odd orbits, let's reevaluate the nebular theory and figure out how we can extend our nebular theory to explain planets around other stars. First of all, let's talk about migration. When a gas giant is forming, it's going to vacuum up all the gas in its orbit, and it's going to keep growing larger as it tugs in gas from inside and outside of its orbit. But the ripples that it makes in the disk can affect the distribution of gas and can affect the gravity. And overall, that's going to allow this to lose orbital speed. And so as long as these streamers and these ripples in the gas are still there, this planet is allowed to slowly spiral in into a smaller orbit, right? But once the nebular gas is cleared out, that orbit is stuck. So we think that explains the hot Jupiters. The hot Jupiters formed outside of the frost line, and then they were allowed to migrate in, and then they got stuck in a close orbit. Another thing that I can mention is that the composition of the planets is going to be altered depending on how long that nebular gas hangs around. If the nebular gas gets cleared out really fast, you might end up with a lot of icy objects or water worlds. But if that nebular gas is bountiful and it sticks around a long time, there's going to be a lot more opportunity for those water worlds to suck in the gas with gravity and turn into gas giants. Here is a real picture of a forming solar system around a star, and based on image analysis, we think that there's actually two planets forming right now with those streamers pulling in gas. So this is an artist's interpretation of what is actually happening in that forming solar system. Now let's talk about close encounters. A close encounter is when two objects get close together and they don't hit, but they get close enough that one object can gain speed and the other object will lose speed. So two planets that were on nearly circular orbits could have a close encounter, and both of them could get elliptical orbits. One of them might get a smaller elliptical orbit, and the one that gained speed could end up with a larger elliptical orbit. I don't have any great examples of planets affecting each other's orbits when they get close, but I do have this animation of how we used encounters to boost a satellite called the Rosetta mission into a larger orbit. And so it's already passed Earth and stolen some of Earth's speed in Mars. Here it swings by Earth again and steals some more of Earth's speed. Swings by Earth a third time to get even more speed. It's got to catch up to this comet out here. So hopefully this at least shows you that a circular orbit can become an elliptical orbit through close encounters. So another way that you might be able to affect a circular orbit and get it to change into an elliptical orbit is through resonances. So over time, Europa and Ganymede have tugged on Io's orbit to make it elliptical, even though it formed from a disk and it had to form circular. Right? So over time, Europa, Io, and Ganymede have lined up enough that the gravitational tugs have pulled Io's orbit from a circle to an ellipse. So the first extrasolar planet was discovered in 1992. So we've come a really, really, really long way, and we're still making leaps and bounds in discoveries. The next big thing might be Gaia, and it's already launched, and it's watching the positions of stars very, very, very carefully. So it's using the astrometric method. it might discover up to 15,000 planets. So check back in several years and see what Gaia has given us. Right? Another one to keep your eye on would be the JWST, the James Webb Space Telescope. It's going to be better than Hubble, but it's mostly designed to look in the infrared light. So this would be great for detecting really, really distant galaxies, but also really good for looking at planets. So maybe we could do some direct imaging. JWST's budget has been cut several times, but currently it is projected for launch in 2018.